There we go. So, Linus Pauling. There we go. There's a guy, again, from Oregon. He went, yeah, brilliant, brilliant man, one of my heroes. He won Nobel Prize. Only 2 people have won 2 Nobel Prizes. I am pretty sure both of his are solo. No, I can't remember now. Anyway, he won 2. You can't win the same Nobel Prize twice. So he won the chemistry one, and then he won the Peace Prize. And Maria Curie is the other one who won 2 Nobel Prizes. So the first one in physics. So she won the 3rd Nobel Prize in 1903 with her husband. And then she won the one in chemistry for doing more work on radioactivity. So we'll see her at the end of the term because we end with radioactivity. So we're going to look at 2 types of bonding theory. It's really weird doing this sitting down. I've never done this sitting down. This is like so visual and I have to be so expressive. So we'll see how it goes. Yeah, we're going to do orbital hybridizations. And then on Thursday, we'll look at molecular orbital theory, which is really complex. It also won a Nobel Prize. So one of the things that I will say to you is both these theories that we're looking at won Nobel Prizes back in the 50s. They're pretty complex ideas, but they're also simple and elegant, and they've helped us to develop like our understanding of molecules, whether they're real or not, right? Whether you believe in matter. So what Linus Pauling, what he did is, it's the idea that we're working with electrons, right? We're sharing electrons. And in that, the orbitals have to overlap. So remember, electrons, right, are zooming around in orbitals. They're not really zooming around, they're vibrations or they're pulses. So they're occupying orbitals. And so this is the idea. These are nuclei. These pictures, that's the nucleus. And that's the nucleus of the other atom. And this is the electrons in the space between the 2 nuclei. So the electrons are in that space in between, and that's what the theory is talking, that all the theories. Now notice they're showing the electron not as a spot, that electrons are not, even though we think of them as matter, they're really pulsing. Same with you and me, we're not really pieces of matter. And yeah. All right. What Linus Pauling was trying to explain is, where do we get the 109 degrees in a CH4? So, right, that's what this says. Where does the 109 degree angle come from in a tetrahedron? Like, none of you questioned me when I did the tetrahedron, right? There's that guy in the tetrahedron. You can make a better one. You know, one of these days I'll come prepared. I thought of that as I was sitting out in the sun. I'm like, oh, I should go make molecules, but I stayed out in the sun. So that's our tetrahedron. The question about the 109, where does it come from? Because nobody ever questions it until we bring this thought up, which is what Linus Pauling asked. If you go back to Bohr's model and all of those guys, those brilliant men who won also Nobel Prizes in physics, if we have our nuclei here, so remember there's the s orbitals. So s orbitals are the electrons are moving in a sphere. So that's our s. And then when we had p orbitals, you guys remember what p orbitals were? That they made the dumbbell shape or the figure 8 or the affinity sign. So they were either along the x-axis or the y-axis. So they were along the x, y, and z axes. So if p orbitals, that's what this is showing. These are p orbitals. Those are, the electrons are in this area, but they're all at a 90 degree angle. And so how do we get 109? And the other question is, if we go to carbon, if you go back again to last term, you don't necessarily have to write this down. This is like where the puzzlement is, and nobody questions it until like the teacher brings this point up. But if you remember last term when we did orbital theory, if we drew carbon, we would say 1s2. So this is for carbon. We would say 1s2, 2s2, 2p2. That's the 6 electrons, right? So 1s, 2s, and then 2p2. And so if we look at the 2p2, you remember there were 3 orbitals. You guys remember this from last term? And so there's 2 unpaired electrons. So why carbon makes 4 bonds, period. Like in all these beautiful molecules, all the computer imagery and stuff, carbon makes 4 bonds. The whole world of biology is based off of that idea. So where does it get 4 from? And that's what Linus Pauling came up with, this idea. These are always theories. They can never be anything more. That's the beauty of electrons. It can only ever be a theory, but it's a really good theory. One of the things, which I wrote here, because I guess I want to make sure that I remember to tell you that every year, is that the geometry, geo means the geometry has to minimize the repulsion. And so the electrons, when we have the overlap, we have to have a point. The overlap has to be a point where we don't get too much, and the nuclei can't get too close and they can't be too far apart. Before I go into where the CH4, actually, let's go ahead and do the CH4. So what happens is if we do carbon, sorry, I'm trying to think the best way to say this, 2s2, 2p2, right? So we'd have the helium, the 1s2 we don't care about. What he said is you take what would have been the 2s and the 2p, and actually, I'm going to erase because I told you I'm just doing this on the board. And so for 25 years, my neurons are thinking about how I would do it on the board. So this is the 2s and this is the 2p. The 2p is a higher energy, so there's more potential, more happening. What he said is they hybridize. So that's this word. We're going to see orbital hybridization. So we're going to make hybrids. And they hybridize. So the number of lines is going to stay the same, but they come to a point in between. So we now have 4 lines, and they're all the same. So we hybridized the 2s with the 2p, and we made something called sp3. So we took 1s. So if you take 1 and you add 3, you get 4, and that's what this is, an S and 3 Ps. All of these are called sp3, 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 and they're all equivalent. And that's where the tetrahedron, this is where the 109-degree angle comes from. Yeah. And you have 4 electrons, the 4 arrows. Since these are all equal, they will each get 1 arrow. So you guys remember those rules from the end of last term when we did electrons? What we're doing now is we're taking the atomic theory and we're putting its molecules into molecular theory. And so we're looking at how this is possible. So you now have 4 unpaired electrons, and that's where CH4 comes from. And I thought I had a picture, kind of do on the next page, but the idea would be that you have the carbon, this probably, or my little guy here does a better job at showing that. Now, before I go on, so with NH3 and H2O, it's the same idea. We can actually do all of these since I made the space. So with nitrogen, we would have 2s2, 2p3, right? That's our 5 electrons. So we'd have the 2s and the 2p. Should be bringing back fond memories. Those of you at 151, you should be like, yeah, this is great because we did it at 151. We're doing it now. And so these hybridize in the middle. Just a real quick comment. You're not going to show what I'm doing right now. You're never going to show it this way. This is just building us to where we're getting to. And so these are sp3. and there's 5 electrons. So when we draw NH3, when we do the Lewis structure for nitrogen, nitrogens pretty much always make 3 bonds, and they have that lone pair. That's the lone pair. These 3 now have a place to bond because they have an empty spot. So that's what's going on here. The CH4, each one of those is going to bond to a hydrogen. And so there's no lone pairs on the carbon. And then if we go to water, water, of course, looks like this. You can draw it as straight across, but water always has that beautiful kink. And if we looked at oxygen, oxygen is 2s2 and then 2p4. And so these guys hybridize to make the 4 sp3s. So that's what it's called. And how you write this is actually important. So it is a lowercase s and p, and then that 3 is a superscript. That's the name of the orbital. So that's the name of the hybridized orbital. And probably thinking, she says this before, but you guys again have been with me, so you kind of know that it does come all together. That this lecture tonight, the first half hour, whatever, everybody's always looking at me with like the look of the deer in the headlights. And then as we get through it, it's like, oh, that was really easy. This theory just explains everything we did last week. And so it ends up making last week make more sense as we get through it. So this is anytime you have the tetrahedral Vesper, you have an sp3. And we're going to see that. So like your worksheet, the wrong worksheet, if you printed the wrong worksheet like Sunday or Monday before 10 o'clock, I don't know how many of you are actually awake before 10 o'clock on Monday. That's what I was gaming on. But anyway, it's going to start having another column instead of just Vesper and bonding or polar nonpolar. It's now going to say hybrid orbital, and that's where we would be writing this in. So when it hybridizes, we have 6 electrons. So that's how we would show the 6 electrons now. And again, these are the lone electron pairs. So those that I'm circling, those are the lone electron pair on the oxygen. And so it only has room for 2 bonds. That's why oxygen doesn't want a triple bond. It can make 2 singles, it can make a double. All right. I'm gonna, so I don't have to keep going back and forth. Let's finish this page. So I want to talk about a sigma and a pi bond. This is actually really important, and then half of you will get it wrong on the midterm. And I don't know why. I think it's more our nature of we create what we think the bonds are, and then we're going to stick to it, even though that's not correct. So a sigma bond means, a bond means overlap. A sigma bond is overlap between the nuclei. That's what this picture shows. That's a sigma bond. The problem is, when you guys see me draw, say something like this, carbon, oxygen, CO2, you guys think there's 4 electrons. You're like going, oh, well, that's a double bond. There's 4 electrons. All 4 of those electrons are now crammed in there. That's not what it is. That's not possible because electrons all have a negative potential and there's no room for 4. There's only a spin up and down. So the idea of magnetism is we can't have 4 in there. And so we're going to make what's called a pi bond. The symbol for sigma is this. It's like a circle with this little tail at the top. And the symbol for pi, it's a capital pi. So it's not the same symbol that you learn in math. But, you know, pies, you should make a pie for a pi bond. I honestly don't care if you make it a little curly pie, but that's why that symbol in the font I chose, it comes out funny. This is that the overlap is above and below. Remember, electrons behave as pulses, so it's above and below. That's what this is. That's a pi bond. The area between the nuclei. So again, the key is that there is still an overlap. It is also unhybridized orbitals. Sorry, unhybridized P orbitals. That's why they called it pi, because it's a P orbital that did not make the cut here. And yeah, we're going to see that on the next page. That's my next example. This picture is showing you, so these are P orbitals, and when they overlap, if the P orbital is along the x-axis, it would make a sigma bond. If it's along the y-axis, like this is showing, and they overlap, they make the bond. So the 2 electrons in the pi bond are here and here at the same time. It's not that one is above and one is below. You can't think like you think the world looks, because it doesn't look like that at all. And once you can see that it looks like this, that's when miracles can happen. And that's what some pretty famous people were able to do. The thing that's interesting is they all went and meditated for 40 days in the desert. So it just depends who you're a fan of. They must have all just been really dehydrated. All right, we're going to make a chart and then we're going to look at examples here. So 2, 3, 4, 5, 6. That is, if you had 2, we call it linear. If you have 3, we call it planar triangle. If you have 4, we call it a tetrahedral. So the 2, 3, 4, 5, 6, this is the number of clouds around the center. Again, I'm going to call them clouds. They could be lone pairs or they could be bonds around the center. If you have 5, you may remember the name. Starts with a triangle. Yeah, it's a triangle bipyramid. So you have to, just a reminder, don't just say bipyramid. Make sure you tell me it's a triangle bipyramid, because number 6 is actually a square bipyramid, but nobody calls it a square bipyramid. What do they call the 6? You don't have to have these memorized. You guys get notes.
Octahedral.
Yeah, it is an octahedral. Same here. Don't just say planar. You have to tell me it's a flat. Planar just means flat. It's a triangle. By the way, the word planar is spelled with A's, but half of you will spell it wrong, so it's all right. It's not a spelling class. I spell wonderfully too. All right, bond angle. Bond angle, so this is the VSEPR geometry. Then we get the bond angle. So linear, of course, is 180. Planar triangle is
120.
Yeah, you all wrote that already, right? 120. Tetrahedral, I'm pretty sure you all know it without having to look at your notes. 109. Oh, the trigonal bipyramid's the trouble one. Triangles are 120, and then the bipyramid part makes it a 90. That's the funky one. Octahedrals are 90. So again, I just wanted to comment, just keep it simple. Don't go with Google where they're putting 107.4 degree angles. I mean, that's wonderful that people can be that precise with their measurements. And yeah, some of you gave me angles like with 6 sig figs. That was fascinating. All right, so we're adding one more piece here, which is the hybrid, orbital hybridization. So that's the new piece today. So we already did the tetrahedral. That's SP3. So there has to be 4 pieces. All of them are going to start with S. So go ahead and write your little S at the beginning of every single one of them. That is always the first thing that hybridizes, is the S. Now for linear, we have to get a total of 2. So it's just SP. The S hybridizes with 1 P, and that gives you 2 things. So for planar, it's called SP2, because the S hybridizes with 2 P's. That gives you 3 orbitals. SP3. Now you're going, this is really easy. SP, SP2, SP3. There's no such thing as an SP4. Why?
Because it can only have 3 orbitals in the P.
P's have only 3 orbitals. That's what the theory, that's what the math says. It must be true. So what comes after P? D. And so we take the S, we hybridize it with the 3p orbitals to make it all the same, and then we only need to bring in 1 D. That gets us to 5. So the S and the D and then the 3 P's. So how do we get to 6? It's a pattern. So the S hybridizes with 3 P's and 2 D's. That's what it's called. They're all lowercase letters. The 3 and the 2's are superscript. We just don't show the 1 for the S. So we're going to make one more column. Hopefully you left room for one more column. Is unhybridized orbitals. Yeah. All right. Let's write sideways. Nope, that's not going to work. Let's just do it here. So this one has 2 p orbitals. And this one's going to still have 1 p orbital. And this one's going to have 0. And this is unhybridized. That's what I was trying to write. You can squeeze it in yours. So on the SP, there's always 3 p orbitals. With the SP, only one of them hybridized. There's 2 left. This goes back to what I just talked about. You can make a pi bond if you have an unhybridized p orbital using this theory. Again, I'm a biochemist, so this theory rocks for me. All right, we're going to see an example. And these pictures, which did print in color, which is great, are trying to show you that. And these are actually wonderful pictures. If we drew C2H4, what the molecule looks like is a double bond and then 2 hydrogens on each carbon. You can count your electrons, do all of that. One of the things with the organic chem lab, carbons make 4 bonds. Once you can get that like sunk in your brain, that's Silicon is the same thing. Silicon is like the basis of all the crystals that we all love, that a lot of people, yeah, there's some pretty cool stuff you can do with it. And it's also the basis of our computers and our cell phones is silicon. And it's right below carbon. It makes 4 bonds. All right. So what has happened here? You can write this part down if you want or not. That's what this picture is showing. That's the sigma bond. So these are sigma bonds, the yellow ones. The purple is the pi bond. This double bond is 1 sigma, 1 pi bond. That's where you get 2. So you have an overlap in between and an overlap above and below. What the theory is saying is going on, this part that I'm going to do now, this is what you would have to tell me is how many sigma, how many pi. So in this whole picture, there are 5 sigma and 1 pi bond. So each of the carbon hydrogens is a sigma bond, and then the double bond is 1 sigma, 1 pi. So this is what the double bond really looks like. This is why on your study set, we had the question about, right, which bond is shortest, which bond strongest. Double is always stronger than single. And up here, triple is even stronger because there's so many electrons and because of how they're overlapping. So there can only be 2 electrons in between. The other electrons are like that. When you get to a triple bond, that's what this is showing down here. You have 1 bond overlap in between, 1 bond above and below, that's the darker color, and 1 bond on each side. So it's like enveloped in electrons. So extremely strong, extremely susceptible to damage. Do I not have where I go off on that? Sorry, I usually go off on the topic of, yeah, I do. All right. What's going on here, and again, you don't have to write this part down, is that if we go back to carbon, which had the 2s and the 2p, right? So it had 2 electrons, 3, 4. What happens when it hybridizes is you only got 3 orbitals that hybridized. So this is sp2, and you still have p orbital unhybridized. So you still have 1 p orbital up there. So the 4, yeah, that p orbital is your double bond, is one of the double bonds. It's the same idea here in CH2. Oh, the only way it works out is you have to put a double bond. So the questions that you will see, and the whole next page is practice. And so by the time we get through that page, you'll have this, is I will ask you, give me the angle of the carbon. And so you should be able to look at that carbon and say, okay, that's 120 degrees. But now you'll see the question say, what is the hybridization of the carbon? If it's 120, it's sp2. So there's 3 things came together to make this work. And then I'll ask you how many sigma, how many pi bonds. In this theory, sigma is every bond is 1 sigma. So we have 3 sigma. A double bond is 1 sigma, 1 pi. So we have 1 pi. We're going to get bigger molecules coming up. All right, C2H2. The only way it will work out is you have to have a triple bond. So this triple bond is 2 pi bonds and 1 sigma bond. That's what the picture is trying to show, is you have an overlap in between, and then the overlap in front and back and above and below. So the whole picture is 3 sigma, 2 pi. The bond angle is 180 degrees, and we say this is sp. Where the pi bonds came from. So that would tell us the single bond is sp, the pi bond, or on each side of the carbon, the sigma bonds are the sp. So the pi bonds came from the two unhybridized p orbitals. So the overlap is the x orbital, the px orbital, and then the py orbitals overlap above and below, and the z orbitals in front and behind. You can ponder that. All right, we're gonna do one more. So again, back to last term, this is how myself as a biochemist, because we look at the molecules. So this is saying the carbon has 3 hydrogens. So always a single bond. And then we have another carbon. Now, oxygens actually really don't like each other because they're greedy. So it is not oxygens in a row. That is like going to blow itself apart. What this means is you have a double bond to oxygen and then another oxygen and then a hydrogen. And dots always on the oxygens. That's what that looks like. So, given that picture, how many pi bonds? Pi bonds are easy. You look for doubles and triples. I see 1 pi bond. Now, how many sigma bonds? Works so much better when we're live.
7.
7? I count 7. Questions. The next page should answer the questions. Anyway, this is what the theory, and this theory, why Linus Pauling came up with this, is it explains all the stuff we did with Lewis structures. The thing why we draw them as Lewis structures is his structures are much less cumbersome than Linus Pauling's way of drawing the structures. So the next page, you are going to, these are drawn. You're going to count your sigma, count your pi bonds. You're going to tell me the hybridization of the carbons. You're going to tell me what's the most polar. Or you can take a 5-minute break. So I'm going to pause recording. Do this. That's something actually I miss with the whole class because I can only see a couple of you, but when everybody's there, we can all get involved. I don't know why that question mark is there. So sigma pi bonds. Double bond means we have 1 pi. Can be a banana cream pie, whatever kind of pie you want. And then, so something I didn't mention, this CH3 means that's 3. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Do you guys get 12? Is there 13? 12? Max got 12. Did anybody else get 12? Okay, let's go with 12. I think this is the video I had to make. No, I had to pause it and make sure I had them right because I was not going to videotape myself again. All right, the hybridizations of the carbons. If a carbon has 4 single bonds, it's sp3. 109 tetrahedral. We're doing hybridizations now. This carbon down here is also sp3. So it's got 3 hydrogens. You can leave it like this or you can draw around it. This carbon is sp2. So the double bond, cut it down by 1. All right, I only asked about the carbons and then what is the most polar bond? Look, don't see fluorine. Fluorine didn't show up in any of these. Look for oxygen, hydrogen. If you see OH, that is your answer. That is our most polar. This is going to be where hydrogen bonds come from. And so our topic next week is what's called IMFs, or intermolecular forces. And hydrogen bonding is a special, it's not a bond, it's an attraction. It has to do with this. This is a huge polarity. There's a big pull, tug of war going on there. And then I ask you if it's hydrophilic or hydrophobic. This one is very hydrophilic. So hydrophilic is going to be the heart. It's got lots of oxygens and nitrogens, especially OHs and NHs, OH and NH. So you're looking for NOF. Actually had my NOF, NO and F. I don't know where I put it. There it is. I don't know if I can put it on with my headphones, but the gnome's hat, right, is a NOF, and it's gonna fall off because my headphones. So this one definitely, because there's so many oxygens, very water soluble. There's often somebody who's a bodybuilder in the class, and they'll pick like one of the amino acids as their topic. So that's possible. All right. Wow, this is going to have a lot of double. So count your double bonds. That's your pi bonds. So we got 5 pi bonds. All right. And then how many sigma bonds? So the hexagon is 6 plus 6 more around it, 12, and then 13, 14, 15, 16, 17, 18. Max got 18. Somebody else get 18. We're going to go with 18. All right. And then we're doing the hybridizations. The 1, 2, 3 was, oh, that's our bond angles. That's our hybridization. So actually every single carbon is sp2. Every single one is an sp2. Every carbon has 3 things it's connected to. Every bond angle is then 120 degrees. So in your study set, you're going to see a lot of these questions where it's going to have the picture and it's going to ask you to count, ask bond angles or hybridizations. I didn't ask bond angle, but it's good to do that. Like here, if it's a sp3, it's always going to be a bond angle of 109. The most polar bond, there is only one polar area. There's only one oxygen. So the carbon double bonded oxygen is the most polar. This guy is hydrophobic because there's just too many carbons. Carbon, hydrogen is nonpolar. They don't like water. You need NOF. NOF loves water. And we only have one oxygen and far too many carbons. So it's just this little polar area, the water is going to be attracted here and nowhere else. All right. You can pick the molecule and a spice if you're somebody who wants to spice up your life a little bit there. You should put that as an extra credit. Have you guys do some good cooking. All right. I did last term when I did 105, my organic chem, they did a lot of kitchen chemistry. So I'm going to ponder this, how I can get, maybe I'll have to change something. So 1, 2, 3, 3 sigma, I'm sorry, 3 pi bonds. So you just look at the double bonds and every double bond counts as 1 pi. And then, okay, so I did something here and we have to go through this. Every corner that doesn't show what it is a carbon. So we're going to write them in. Those are carbons. Oh, Major got kicked out. He's coming back. Anyway, every corner is a carbon. In the video on the Organic Chem Lab, it's, it's going to rain one of the days, or chance of rain. So watch it, get it over with, do the lab. It will change how you view all this. Carbons always make how many bonds? And they all, yeah, everybody, right? You're all holding up 4 fingers. I'm imagining that. So draw in your hydrogens. So it's a shorthand. We don't show carbons. You have to show anything else. And if you don't show the carbon, they don't show the hydrogen, but they're there. That is going to totally change the number of sigma bonds you probably wrote, unless you knew this trick. All right. That's what this molecule really looks like. And so something that will be very helpful is to make sure you have scratch paper as you're doing things, and you can make a new, or next to it, make a picture. So some people like to really redraw. Your study sets, those are yours. I just looked to see that you made an attempt on it. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. I have 20. Did anybody else get 20? Sure. Yeah. Damon, did you get 20? All right. We're going to go with 20. So 3 pi, 20 sigma. Hybridizations of the carbon. All the carbons that are single bonds, these guys are all sp3s. This carbon is sp. It's a 180-degree angle. All right. And again, I did upload the video from last year. It's just me by myself in the classroom doing this on the board. I want to mention something here. I don't ask it, but I want to go ahead and do it. These pictures are called structural diagrams. They don't show the dots. This nitrogen has a lone pair on it. So this nitrogen is really an sp2 because of the lone pair. The lone pair counts when you're doing hybridizations. If we went back up here to the oxygen, it's not showing, but there are dots on the oxygen. That is an sp3. It's a tetrahedral bent. So you will often have to draw your dots in. Some people get it without the dots, but some students, it does help. The most polar bond. Oh, that's a tough one. It is probably the sulfur oxygen. I'd have to look at a chart. Did anybody look at their chart? I'm assuming it's the sulfur oxygen. If you pick the nitrogen, it could, I think it's probably the sulfur oxygen, because oxygen's so greedy.
It is the sulfur oxygen.
Yeah. Thank you. And then it is probably just barely hydrophilic. We have the sulfur oxygen, we have the nitrogen, we have a sulfur. You have 6 carbons. I kind of feel that this is not the most fair question to ask if it's hydrophilic or hydrophobic. You would be asked to explain your choice. There are a lot of carbons. So there's a lot of carbons, but there's a lot of, there's the oxygen, the sulfur oxygen, there's the nitrogen, there's another sulfur, and so that's probably allowing it to pull. So sulforaphane, the fame to that, Damon probably has heard the word many times because he's going to nutrition. That's the molecule that's in broccoli that makes broccoli like the superfood. Yeah, I had a healing crisis. I had cancer like 7-8 years ago, and my naturopath told me I went completely in natural nutritional way. That's why I meditate a lot. Anyway, not a big fan of Western medicine. She wanted me to eat like 2 pounds of broccoli a day, and I remember I just sat there and I said, "Excuse me, can you back up for a minute? Do you know what you just said? Do you know how much 2 pounds of broccoli? Like, I don't think I could physically get that in my body." And she stood there and she looked at the thing and she said, "You're right." And so I guess nobody had ever questioned it before because nobody had said, but they basically put me on the, I basically was eating like fruits and vegetables, and that was all. I was the healthiest I've ever been. And yeah, so sometimes healing crises are good because it makes you responsible and changes your perspective. All right, it looks like on this one I started drawing. So these are carbons at every corner, and then you have a hydrogen, hydrogen, there's a carbon. You don't have to draw the carbons in, but drawing your hydrogens. So GABA is, there is a drug that a lot of people take for pain that is something similar to that word, but GABA is a neurotransmitter. It is stimulated by meditation, but it helps to calm you down. And so, yeah, one of the, this is not what's in, psilocybin's what's in mushrooms. This must be, I thought that was in peyote. Maybe that's a picture of what, I don't know what peyote, how they isolate it and stuff. But anyway, this is one of the hallucinogens, and that's actually part of how they work. They're either mimicking serotonin or GABA, and your brain gets overstimulated with that. Meditation does it actually, it takes a longer time, kind of sort of to get there, but if you count all your carbons, I apparently got 15 sigma bonds on this one. So 3 for the hydrogen. Most things in our body are actually ionized, a lot of things. And so this nitrogen has picked up an extra hydrogen. It doesn't have the dots anymore, and that gives it a positive. This oxygen has all of its lone pairs. And then this one, I have 16 sigma bonds. And then they would each have, it looks like 1 pi. But my little writing in there, these are hydrogens. So every corner is a carbon, and then you would have to add a hydrogen to make sure all your carbons have 4 bonds. So that's why I have that. I have 8 hydrogens are added here. And on this one, I must have, I have 9 hydrogens total, and then 6 other bonds. So the 3 hydrogens here. So sometimes that's how I split it up, because the hydrogens are always going to be a sigma bond. The hybridization, it looks like, oh, these guys are sp3 over here, and then that is a carbon, that is sp2. This guy would be an sp2, whereas this down here would be an sp3 because it's all single bonds. What is the most polar bond? It is the oxygens. I'm looking if there's an OH, but there is not. So our polar area is going to be, you know, actually I have to think about this for a minute. We have nitrogen, hydrogen. So this area is also polar. You guys will have that electronegativity chart. Mine's like on the other side of my room right now, but and Damon, you had yours. Is the nitrogen, hydrogen, or the carbon, oxygen more polar? Actually, I know these numbers.
Hydrogen is 2.1, nitrogen is 3.0.
So that's 0.9. So it's the carbon, oxygen.
Carbon, oxygen is 1.
Yeah, so they're very similar. They're almost the same. They're close enough for me. So either one, that's both of those areas are polar. And so these are definitely hydrophilic. The first one and last one, definitely hydrophilic. And especially something I never talked about because we haven't really seen it. They're ionic. Ionic loves water. Like this thing is pulsing, it wants water. It's like the Grinch's heart. It's going to grow 3 sizes. Ionic loves water. Always hydrophilic if it's ionic. In our body, most things become ionized. So there's a lot of other neurotransmitters or hormones. So if you're somebody going towards medical field, you could pick medication. You pick a neurotransmitter. You pick an explosive. Nitroglycerin's a cool one because it's an explosive, and then it's also the one that's used for heart issues. So there's a lot of interesting history there. Any questions from this page? Oh, we're gonna be done. We're almost done.
So I just have one quick question. So when I'm looking for the NOS, this is what I'm looking for, hydrophilic.
Say that again.
I'm looking for the NOS. then that would be hydrophilic or hydrophobic.
I can't hear you.
Can you hear me now?
Well, kind of. There's just a lot of background.
Sorry.
Try it again.
If I'm looking for the NOS, I'm not looking for
Yeah.
hydrophilic or hydrophobic.
Yeah, so thank you. So he's asking about hydrophilic and hydrophobic. So you're looking for something that's highly electronegative, so NO and F. Also chlorine. Carbon hydrogen is nonpolar. So hydrophobic is carbon hydrogen. So when you see, since we're carbon based, I tend to be very carbon centric. If you see something that's mostly carbon hydrogen, and so Major, these questions show up on your study set for Thursday, so you'll see several of these on Thursday, and that will help refine it. Yeah. All right, we've got one more page, and then I'll go watch the sunset. I mentioned this last week, so I want to go through it again. This is kind of review of some of the stuff we did last week. Oh, and isomers are on there. So bond order is, I think of it as the average bond. I'm sure you can Google it and get some really highfalutin explanation. So it's the average bond. How you do it is, it's the number of bonds divided by the number of connections or outer atoms. So I think these are the ones that are on your worksheet. So we're basically going to do your next worksheet. So if you count your electrons in SO2, you'll have 18 electrons. If you make your sketch, giving your octet to the outside, right? I think you're all good with that part of Lewis structures. So you count your electrons. Sulfur has 6, oxygens each have 6, so I have 18. Sulfur's in the center. Give your octet to the outside. Before you start doing double bonds, you give 2 to the center. So you use up all 18. But you always want to ask yourself, did I meet the octet rule? And you did not. So we would erase 2 and move them over. So this is SO2. So there is a lot of stuff online that say, oh, the octet rule is not that important. It's only important for carbon. That we want the formal charges to be 0. I haven't bought into that camp. We're going to go with the octet rule just to keep it going. This is a resonance. So to do the bond order, we would say there are 1, 2, 3 bonds, and then there are 2 atoms. So we would say the bond order is 3/2. Or if we average a double and a single, you get 1.5. So it's really up to you if you want to average them or count the bonds, count the lines, divide by the number of linkages. All right, SO3, 24 electrons. Sulfur goes in the center. So go ahead and do your octet for your outer ones. And you want to make sure you do these always in a way you can erase. And then you want to count. We have 8, 8, 8. We have 24. Center doesn't have an octet yet. So for the bond order questions, you got to be able to do your Lewis structures. So we're going to have to make 1 double bond. Again, we have a resonance. So in this theory, it's going to change on Thursday when we look at the other theory. In this theory, a resonance is going to give you a fraction bond order. That's the idea of this theory. So SO3, there are 1, 2, 3, 4 bonds, right? So you count every line, number of bonds or number of lines, if you like that. And then there's 1, 2, 3 atoms on the outside. So it's a 4/3 bond. Or if you average a double and 2 singles, you'll get 1.33. And then this was a question some of you had. If you have that -2, it means you have 2 more electrons. And so what happens here is we don't have to share these two. That didn't erase very well. Remember, so what is happening in a resonance structure is that double bond. That is an unhybridized pi bond. Sorry, unhybridized p orbital. It is an unhybridized p orbital of all 3 oxygens and the sulfur. And so it is actually called, this helps often 1 or 2 students, a delocalized pi bond. On the organic lab video, I talk about it a little bit, but that's what's going on. There was a picture on the first page. Not really. That wasn't the picture I was thinking of. But yeah, that's the idea there. All right, SO3 -2. Same here. It's a delocalized pi bond is what it is. It is a pi bond. On this one, we have those extra electrons and they go on the center. So our bond order on this one is simply a 1. We have 3 bonds divided by 3. If they're all single bonds, your bond order is 1. All right. Bond length, as you increase the bond order, you decrease the bond length, and you increase the bond strength, which is often called the bond energy. That's the numbers we worked with in the first question on the homework. This is true no matter what theory we work with. This piece holds true. The higher the bond order, so going from a single to a double to a triple, highest number you can get for bond order is 3. There is no such thing beyond that. There's no place else for the orbitals to overlap. So it becomes a mechanical constraint. The bonds become stronger and they become shorter. So the overlap starts pulling them in. Those pi bonds pull the atoms together. The comment I want to make for you is pi bonds, because the overlap is above and below, so above below the nuclei, they are very susceptible. So they're stronger, but they're very susceptible to damage. Our cell membranes. So all of you have heard about DNA. You probably learned about DNA. We have become a DNA-centric society for some reason. It's all in my genes. We've become a victimized society. Oh, it's in my genes. Oh, so-and-so had it. I'm going to have it. Oh, my uncle had diabetes. I'm going to have diabetes. It turns out it's not about our DNA. So our cell membranes are the walls. So like your house has walls. If you suddenly had holes in the walls of your house is going to eventually fall down. Our cell membranes are loaded with pi bonds, and they are very susceptible. It's actually important that we have them there, but they're very susceptible to injury. And think of it this way. So if we're holding hands, like we're all in a group and holding hands, that would be like a sigma bond. And then there's no place for major. So major has to step up on top of people's shoulders to be there. That's the pi bond. Major's, maybe he's making our pyramid stronger, but he's very susceptible that he's going to get injured because he's up there like as a flag. And so pi bonds get damaged. They get damaged by ultraviolet rays or X-rays, pollution, because of free radicals will cause damage. So light, oxygen, you know, that's missing from here. Air, oxygen is one of the biggest causes of free radicals and damage to this. This is the whole thing. There's so much stuff on YouTube now about breathing through your nose and the importance of that. And what happens in meditation, you breathe through your nose, you have to breathe slower, and that slows down your heart rate. But that's the whole point of meditation, is you're breathing slower, and so the oxidative damage doesn't happen. There's a really cool study I heard about yesterday. It's a video. I saved it because I listen to it every once in a while when I need to listen. And they did it with chopsticks, but so it was in China. But they had the people put the chopsticks in their mouth. There's 3 different ways you can do it. One way is you would bite on it, so you're just biting on it. The other way was you had to bite on it, but keep your teeth smiling. And then the other way, however, I don't remember how they did it, but you had to like really smile like you're laughing. And then they measured the people's heart rates. And the people who were truly smiling, because of how they were holding like their finger, like you just bite your finger, but the way you're biting it, it makes your whole face like have to be in this beautiful smile, not like a grimace smile. Their heart rates were the slowest, meaning the calmest, because you all know when your heart rate slows down, you're much calmer and stuff. But so all it takes is a smile. And smiles are contagious. That's one of the problems with the masks. So when I ride my bike, I just smile at everyone and say hi. Like Major's really good at that. And so that's why it's wonderful. You guys turn on the cameras and you're smiling. Anyway, so free radicals is an unpaired electron, and they look for a pair. So this is a question, Kobe, you had asked me. On the lab, you're not going to get an odd number. If you get an odd number, you did something wrong. And you should write a note like, I'm getting an odd number, go back and count. One of the things in here it mentions is stress. So when we're stressed, we're breathing faster. And also when we're stressed, we change the vibrations of our body, and that creates a cascade of molecules called the stress molecule. So that would be epinephrine. So if you want to do adrenaline as your topic, there's so many cool studies out there, and cortisol. So if you want to be, that's our stress hormone. So traditionally, if you want to think that like we evolved from the apes or whatever, and we were the hunter-gatherer society at one time, that when somebody attacked you, a tiger really was going to attack you, you had to be able to run. And so our adrenals release adrenaline, and that makes our heart rate go higher. So when there's a real stress, adrenaline is released and you run. And after 2 hours of running, you've used up all the glucose in your body and all the storage of glucose. So you have to have a way to make glucose in case you have to keep running. So meanwhile, whenever adrenaline is released, cortisol gets released. Cortisol is hydrophobic. To get around in your body, if you're hydrophobic, you need a little boat. So it takes a little bit longer. It's the slow boat to China. So cortisol is released from just above your kidneys, your adrenals, and has to make it to your liver. It's not far away, but it takes the slow boat. And then, because it's hydrophobic, it crosses your cell membrane and goes to your DNA and changes how your DNA is expressing so that you can start making glucose from your amino acids. So your proteins, your leg muscles, your gluteus maximus, that's a storage for when you need to make glucose when you have no more glucose. So after 2 hours of running, you're done. If you're fasting, it takes about 2 days. But if you're exercising, like extreme exercise, it's like 2 hours. Anyway, so if you look at people who are really like long distance runners, they have like no muscle because they're like perpetually putting themselves. This is the idea of ketosis. which is actually ketoacidosis. So it's not a healthy state. It's a disease state. It's a backup plan. But meanwhile, your body, so you actually, in this day and age, there was no tiger. You didn't run for 2 hours. It was just somebody who upset you. And 2 hours later, you don't even remember who upset you or the situation. Unfortunately, that little boat can't go backwards. It's a one-way boat, and it's already gone to your DNA, and it tells your body to start breaking down your protein and make glucose. And then your liver goes, what the heck am I doing this for? He's there drinking his frappuccino, latte, whatever. He's got plenty of glucose. And so you store it as fat around your organs, around your liver, and you get, yeah, it's all beautiful how our body was designed and what we do. Or you just stay in a state of joy and love, and that doesn't happen. And that's the trick. So stay in a place of joy and love and gratitude. Gratitude's the key. All right, remember that lab we did? It comes back in like a couple weeks. All right, isomers. I want to talk about isomers. You're going to all listen this time when I talk about isomers, because you're all like, had to do that in the lab, and that was the hardest part for most people. Isomers, we're going to do these. This one I actually did last week, but we're going to do it again, is carbons you put in the center. Whenever you see multiple carbons, we have multiple centers. And we can draw this two ways. We can give each one of them 2 hydrogens and 1 chlorine. And carbon makes 4 bonds, so I'm going to be good. Or we can give one of them 3 hydrogens and the other one 2 chlorines. Those are isomers. Because single bonds, sigma bonds rotate. That means a single bond. So that little blip is there. If you show the chlorine at the top or the bottom, it's the exact same thing, because the single bonds can rotate, because the overlap is just in between, so they freely rotate. This one is going to have a double bond. So these are isomers. We actually had to break a bond of this chlorine and move it over here. So it's something totally different. We didn't just rotate it. We didn't just turn our paper upside down. Turning your paper upside down does not make an isomer. Putting the chlorine in the middle does not make an isomer, because that is totally impractical. It doesn't happen. All right, so here you're going to have a double bond. It's the only way it works. Pi bonds do not rotate. No rotation. They're stuck. That means there's 3 ways we can draw this. We can draw, what did I do? Chlorine. So you can put your dots on your chlorine. That is not the same as this guy. I think somebody is knocking on my door. I can ignore it. Maybe it's a ghost of Christmas past. Which one was the jolly one? Christmas present. I want to be the ghost of Christmas present. He was the jolly one, and he went and ate a lot of food. All right, these are different because the double bond doesn't rotate. And then the third one would be if we put both chlorines on one side and both hydrogens on one side. All right. So we're now going to do polar, nonpolar. Isomers only happen if you have 2 centers like this and different things around the center, or if you have the expanded octet, that means the 5 or the 6. That means you're in the d orbitals. Those can make isomers also. Like these regular ones, there's no isomer for that. Tetrahedrals, they don't make isomers unless we have 2 tetrahedrals together. This is still tetrahedral. It's not an octahedral. This is polar. You're going to see questions where I ask you to show the polarity. That would be one way to show it. This would be polar towards these chlorines. You can draw it however you want, but the chlorines are pooling in all of these. This one here, this is polar. This one is polar. This one is nonpolar. Because of the double bond, it's stuck. So when I did this picture last week here, I put the chlorines across from each other, and then I like flubbered about saying, oh, they're not really across from each other because it's a tetrahedral. A tetrahedral, they're never across from each other. This is sp2 planar triangle. This is flat. This actually looks like how we drew it. These chlorines are across from each other. One more step and then I'll end. This is called cis and this is called trans. I talk about this in the organic lab and then you have a post-lab question about it. But if you've heard of trans fats, which you all have, they got banned. They were banned in pig food in the 70s. Pig farmers knew in the 70s that margarine was killing the pigs. And we didn't want the pigs to die before they became really fat and we could slaughter them and make them into ham. So it was banned from pig food 40 years before it's not actually banned from our food. They have to label it. Oreos cannot be made without trans fats. If you're an Oreo fan, they can't get it the right texture. I did not grow up. My mom never bought us Oreos, and so I'm grateful for that. She put ding dongs in our milk. So that they're called something else here. So on the East Coast, they're like different names. They're little black things with. That's what you guys call them, right? Ho-hos with the white cream in them. It's amazing. I'm sometimes that any of us are still alive with the stuff out there. Anyway. The trans fats versus what we would want, which is cis. That's another possible topic. So if you have no idea about topic, talk to me. You have to have one by next week because our presentations are like in 2 weeks or something. All right, I am done. I will stay around though. So if you want to work on your worksheet, I'll turn on a light. Oh, I should stop recording. Okay.